the last section on chapter 4 is 4.5, and that is exponential growth and decay. So the idea for exponential growth and decay is that we use the ideas of exponential functions to model, and that means to see what is the growth or decay of substances. Usually this is used for population models and for radioactive models. I'm going to do 2 examples, one of each, and then that will end section 4.5. So exponential growth and exponential decay, they both use the same model. So this formula, if you notice, is very similar to the compound interest formula, the one that is compounded continuously. A is the final amount, A sub 0 is the initial amount, K is the rate of growth, and T is the time. E is the usual number, 2.71828. So again, K is the rate of growth or decay. And T is just the time in whatever the unit may be, maybe years and maybe anything else. So let's start with an example. In the year 2000, the population of Africa was 807 million. In the year 2011, it had grown to 1,052 million. So usually growth is exponential when it deals with population. And so one of the questions will be, find the equation that models growth. So what this means in English is find what is the equation that we can use to find out what the growth will be for any year. And so what we do then is, I'm going to write the solution in red. Now, we know that in 11 years, the initial population was 807 and the final population was 1,052. So what will that do is that will give us an equation that we can solve for the letter K. So I'm going to write the information. So A is the final amount, so it's 1,052 million. A sub 0 is the initial amount, and then e to the k, we do not know what k is, but we do know what the time is, that's 11. So in other words, we can rewrite it as 1,052 equals 807 e to the 11k. So our job is to find what k is, the rate of growth. Anytime we have a population problem like this, always find the rate of growth first. And so to find the rate of growth, we use the initial information that they give us. Well, that means that if we divide both sides by 807, that will give us one more step into simplification. So that means that e to the 11k equals 1.30359. Again, remember, how do we solve an exponential equation? Well, the first attempt is to change it to the same basis. If we cannot have the same basis, what we do is we rewrite it as a logarithmic form. So to change this to a logarithmic form, we want to say the natural log of 1.30359 equals 11k. So what we do is we find what is this logarithm, so that gives you 0.265124 equals 11k. And so to solve for the letter k, we divide both sides by 11. And so that means that k equals 0.02410. So what does this mean? That means that the rate of growth is 2.4%. Now, of course, we were not looking for the rate of growth. This is only an aside, but this will give us the equation that models the growth, because the equation now is the final population, depending on the time, is the initial population is 807, e to the 0.02410 t. So this is the equation that will help us for any other information. And so the next part of the question, what they have is they say, by which year will Africa's population reach 2 billion people? So now what we want to find is, so I'll rewrite that. So given that the formula is A of t equals 807 e to the 0.02410 t, then now the question is, how long will it take until the population reaches 2 billion? And remember that 2 billion means 2,000 million. So this is the final population, and so what we want to know is how long does it take. So we write 2,000 equals 807 e to the 0.02410 t. So what we want to find is what is the value of t. Now that means that we have an exponential equation, and before we have an exponential equation, what we would like to do is to make sure that we isolate the exponential form. So that means that we shouldn't have a number in front. Well, that means that we have to divide both sides by 807. So divide the left and the right by 807. And so we get 2.478314 equals e to the 0.02410 t. But remember, now we have an exponential equation. To solve an exponential equation, we change it to natural log form. So we're going to write the natural log of 2.478314 equals 0.02410 t. So now we find, using a calculator, what is the natural log of 2.47. And so that is 0.90757 equals 0.02410 t. So to find the value of t, we divide both sides by this coefficient. And so dividing both sides, we get that t equals 37.65. So that means roughly 38 years. So it's 38 years from the year 2000. And so that means that the population would reach 2 billion in the year 2038. Okay, so this is exponential growth. The next application of these equations is with exponential decay. So here is one example. Before we do the example, I just noticed that we need one extra term, and that is called the half-life of a substance. So the half-life of a substance means that you found the amount of time needed for that particular substance to decay to half of its original amount. So what that means, for example, if you start with a substance, whatever the substance may be, that has 100 grams, or 100 pounds, 100 ounces, anything you want. Let's say that it takes it 25 years. So if the half-life is 25 years, that means that it takes 25 years for this to become 50 grams. Now, one thing about radioactive materials is that they decay into something else, but you still have the same mass. Now, for another example in your body, if you take a drug, like an aspirin, for example, your body will try to metabolize it, and so what that means is that in a certain amount of time, you will not have the same amount of aspirin, it will be metabolized into something else. And so that is one way to find out how long it is until you need to take more medicine. So we'll do one of those examples. So here's an example of drug metabolizing. So the half-life of aspirin in your body is 12 hours. So that means that if you take, for example, a pill of aspirin in 12 hours, you will have half as much as what you started with. So the question is, how long will it take for the aspirin to decay to 70% of the original amount? So what we will do is we'll use the same, we will be using the same formula. So we will use the same formula to solve for t. So Remember, like we said earlier, in any of these decay problems or growth problems, the very first thing that we have to do is find the rate of growth or the rate of decay, which is in this case. So we use the information that the original amount, even though we do not know how much it is, but we assume that it's 100%. Now, of course, the final amount is 70%. So I'm just using the numbers as such. I don't need to write a decimal because eventually will work out. Now, notice that the half-life of aspirin would be the amount, and that's why I should write 50 in here, excuse me. I'm going to write 50 because that is 50% in the amount of time, that is 12 hours. If I use this information, it will tell me what the rate of decay is. So again, using this formula, A is 50, the original amount is 100% worth, K times T, that means 12K. So again, the very first thing that we use is the rate of decay, the half-life, in order for us to find the rate of decay. So what we do is we solve for the letter K, we divide both sides by 100, and when we want to solve for the letter K, we write as a logarithmic form. And so that means that E has to go away. I'm really sorry, I forgot to get rid of E. So from here, we write the natural log of 1/2 equals 12K. So from here, it should go directly here. I forgot to get rid of the E once I write as a logarithmic form. And so we find what is the natural log of 1/2. So you will get negative 0.69314 equals 12K. And so now we divide both sides by 12. And that means that K equals negative 0.05776. So what this tells us is that the rate of decay is this, and now we can use the equation. So notice that the rate of decay is negative, and that's because you're going to have less at the end of 12 hours than what you had at the beginning. So now, using this equation, we ask ourselves, how long will it take, we want to solve for T, for the aspirin to decay to 70%. So that means that the final amount will be 70%. The initial amount is 100%. E to the negative 0.05776 times T. So notice that what we're trying to do is solve for time, because you're being asked how long will it take, so we're trying to solve for T. So how do we solve for T? Well, again, when we have an exponential equation, we write it as a logarithmic form. So the natural log of 70 equals, well, I'm going to write 0.70, and the reason why I will write 0.70 is because we have to divide both sides by 100 first. And so that will give you 0.70, and then the natural log of 0.70 is equal to negative 0.05776 times T. So the last thing to do is to solve for T. So the natural log of 0.7 divided by negative 0.05776, that would be t. Now, if I look at what is the natural log of 7, of 0.7, the natural log of 0.7 is negative 0.3566, and we're going to divide by negative 0.05776. And that gives you 6.17, so that means that the time is about 6 hours. So we were able to find how long you get for the aspirant to decay to 6 hours. So these are the basic problems that you will see in your homework. That means the growth and decay problems for section 4.4. We're not required to go over logarithmic growth. So on MyMathLab, now you should be able to do sections 4.1 through 4.5. So now, as a summary of what we've done, we've done a review of chapter 4, and we finished sections 4.4 and 4.5. And so here's the schedule. So test 2 will include sections 2.7, 4.1, 4.2, 4.3, 4.4, and 4.5. What you should also do is review on page 539, and then do exercises 1 through 28. Please check on Blackboard for instructions. I will post these notes as well on Blackboard so that you can have another set of resources. Please again let me know if there's any questions. If you would like to contact me through an office hour, we can do this via Blackboard Connect. I think that's the name of the application, and we can answer questions via video.